Okay, well, let's start the webinar. Thank you everybody to join this webinar. Today we're gonna talk about how to transform the raw resistivity data into actionable insights. Basically, we're gonna go through all the process of log squaring, forward modeling, resistivity, and we are gonna talk and show some case studies. Okay, my name is Rómulo Cuevas. I'm Senior Technical Manager of Europe. And with me is Jair Sarmiento. He's a Senior Technical Advisor. Please, if you have any question, just send it into the chat and we can reply after the presentation. So this is the agenda. Basically, we're going to go through assessment of Earth model and predictive resistivity responses based on a customized geological scenario. Basically, the first stage of how to, build an Earth model and run different tools. And then the understanding of inversion outputs in a geological context. Then we're going to talk about evaluation of case studies integrating geosteering techniques. Okay, so let's start with the assessment of Earth models and predictive resistivity responses based on a customized geological scenario. Why we say customized geological scenario is because this stage is, this process is in the stage of like pre-job. So you need to, so the geologists build a scenario based on their data, on their knowledge of the reservoir, like maybe there are some faults, maybe there are some lateral transition, maybe they're expecting some even like transitions in the resistivity based on offset well logs they have around, right? So there is a customized geological scenario where you can build your Earth models and test different tools. So during this demonstration, we are going to clarify questions like what is an Earth model and how do we build it? How can forward modeling predict tool responses? How does geology influence resistivity responses? Can we compare different tools in the same scenario? Okay, let's go and check that in StarSteer. Okay, so in StarSteer, I have a project here, a simple project. As you can see, I have a lateral well. This blue trajectory here is my lateral well. I have, as you can see, this dash green line is my grid. So my structural like interpretation that can come from the 3D model or seismic interpretation. So this is my structural trend it's a kind of a soft anticlinal, as you can see, and this is my lateral well. So then I have offset well with some logs already locked. So we have gamma ray, resistivity, density with these properties in the reservoir, in my reservoir air sun. So first of all, so the first stage basically is to evaluate or create the log squaring. So what's log squaring? So basically the log squaring is the way I can take this resistivity information and add it to my cross section. Okay, so the way to do it, I need to select my tie well log resistivity. Okay, and I click here, create log square. So the log square is gonna appear here in my tie well log. So I'm gonna just put it here. I'm going to put this over here. I'm going to highlight this so you can visualize it better. Right. So this is my log square, and I can actually fine tune the thicknesses and the contrast. So basically, I am creating a log with different thicknesses. So you can see if I move here, the contrast, I increment it or decrease it, the contrast change. So it's higher and lower, and the thicknesses also change here. So I try to make kind of a contrast and thickness that match with my resistivity log from the offset well, so I can add this data into my cross section. Okay, So once I'm agree with this, I can click here, update Earth model. Okay, so this Earth model is going to appear in my interpretation. I'm going to put it here so you can visualize it. Right here also. And I'm going to remove this lock screen. Okay. I'm going to increase also here the thicknesses so you can visualize it better. Okay, so this is my Earth model. As you can see, well, my Earth model, I have here just like a flat layer cake with the information I add from my log square. So I just add thicknesses and contrast into the Earth model, right? But then I can actually fine tune a little bit more. I can adjust it a little bit more, make it a little bit more real, like as I'm expecting here, you know, trying to match a bit more my thicknesses and contrast in my resistivity log, from my resistivity log. Okay, something like that. Yeah, high resistivity peak here below the base. Okay, because I have a big density response over here, as you can see. So okay, then this is the like inputs of my Earth model. So I try to match kind of pretty well with the resistivity of my offset well log, and these fixtures or these properties enter here into my Earth model. So once I'm agree with this Earth model, like I'm good with this, I can adjust the structural trend here. So I can go to my tie well. I'm gonna create some horizons there based on grids. Some grids, and then I can drag and drop the grid. So this is the dash blue line I have here. So I just drag and drop it here into my top, and then create and replace. So I have, this is now the interpretation based on my grid, and you can see we have the resistivity properties inside. Okay, good. So once we are okay, agree with that, so we have what we have. We have the Earth model with the thicknesses and contrast and resistivity contrast inside of the Earth model, and then the Earth model with the structure that we are expecting. This is the fixed scenario I have, anticlinal there, right? So then I can go and proceed with the next step, which is the forward modeling. So the forward modeling is the way we can create, so we can evaluate these different resistivity tools available in the market, and we can see how these tools react in this scenario with this resistivity contrast that are in my cross section, right? So I'm gonna select this tool, and then these logs here. I have some azimuthal logs, some bulk resistivity logs, and some signal strengths and target direction logs based on this tool. So I'm gonna click run, and I can now visualize these logs in my horizontal track. So I'm gonna just drag and drop these bulk resistivity logs over here. I'm gonna drag and drop these signal strengths here, and this, let me just put it, refresh the scale and the target direction over here, and put it from 0 to 360. Let's put it top points, lines. Okay, so then, okay, how we can interpret this like resistivity response. So basically we have, so in the first track I have the bulk resistivity data, right? So I have some you know, logs, and these mnemonics you have to learn it from the tools. So different tools have different mnemonics, but basically there are some, in the bulk resistivity, there are some attenuations at phases that are measuring the resistivity contrast around the bore, right? So I'm gonna just highlight for instance, the faces, and I'm gonna change the colors so you can see the difference between phases and attenuations in my bulk resistivity. Yeah. Okay. And also for the signal strength, this is the low frequency. Let's put it like in blue, and high frequency, let's put it like in red. And the target also like a low frequency, let's put in blue, and tax this one in red. Okay, so basically I'm just customizing here the colors, so it's easier to interpret. So for instance, what's going on here? So when my wellbore is approaching to my reservoir, so I'm having this resistivity contrast, right, based on my Earth model. So I'm getting some like artifacts, or some responses in my resistivity logs based on this tool. So as you can see, there are some resistivities that react first and resistivities that react before we cross the contrast. So the red logs here are the attenuations, right? They tend to read deeper, and the blue ones are the phases that tend to read like more sharper, the contrast, like the proper contrast, basically. And there are some artifacts like shoulder effect when you're approaching here to a contrast, the polarization horn, this polarization horn when you are crossing two different mediums, like two different layers with different resistivities. And then when you are, it's getting like kind of an isotropy here, when there are some separation between logs, or the logs are reading different resistivities around because it's still kind of near to the contrast, and then the logs here get almost flat because they are measuring one resistivity contrast. Okay, so you can see all these behaviors and understand what your borehole, your trajectory is crossing, basically different resistivities with different thicknesses. Then the second track show you the target direction. Basically, it's measuring from where the resistivity contrast is coming. So it's actually, in this case, it's like from 0 to 360. It's like the tool phase, azimuth. So the 360 and 0 is actually the top, and 180 is the bottom. So you can see from where the resistivity contrast is coming. And then we have the signal strengths, and that show us when this strength or the signal is rising, is because the contrast is near to the borehole, and when it drops, it's because there is not contrast around. So this is how you can interpret, and different tools have different ways to interpret these responses. Okay, so well, this is how this tool will read the contrast. You can also measure here. Okay, for instance, over here in this area, you can see from here the attenuation is starting to read that something is coming from the bottom. So you can actually kind of have an idea how far this tool can read just using the forward modeling, like 1.5 meters from the borehole. You will see this detection. Okay. And so then you can also create another kind of scenarios. For instance, if you think okay, from in the last part of my lateral section, right, my resistivity is going to change because I have another tie well that suggests, okay, this thickness is going to be wider, or I have less resistivity contrast in some areas. So you can modify basically your Earth model in different areas. As you can see, okay, in this segment I'm modifying it here, and so on. So you can play and create a tie scenario that's, you know, match with your structural and geological properties based on your 3D models, right? Also, I can maybe, let me go here, let's go to steering, and I can, you know, change the, as you can see, once I, you know, like change the properties, also the logs react at once because they are dynamics. They are reacting on the fly. Depends how I'm crossing my structure. So you can say, okay, you can have different scenarios. What happens if the anticlinal is not that lower in this area? It's like kind of more, you know, high in this area, or what happens if I have, you know, a small like fall can be, you know, you can create a fall, or you can create like what happened, what's the answer, or how the resistivity will react if I'm crossing the base, or how it react when I'm crossing the, I don't know, the top at the end, how, you know, so this kind of, you can put different scenarios and check and see how your resistivities react and how far they can detect this contrast, basically from the top, from the bottom. So once you agree with your scenario, you can convert these dynamic logs into real logs, like kind of fixed logs. So once you convert this into fixed logs, you can keep going here and create the resistivity inversion using that tool. And so basically we have a capability here to create stochastic and deterministic inversions. Then you can see how the inversion will look like using these resistivity logs. Okay. So, okay, let's keep going. I'm gonna come back here to the slides. So now let's talk about the understanding of the inversion. So this is the next process. Once you do the Earth model, you create your scenario. And so this is, then you can create your inversion and see how it looks like with one or different tools. And then in real time, well, you use the real time the data, resistivity data, to create inversion. And then Jair is going to show you basically the understanding of these inversions and how to read it and how to see like the dips, or, you know. So we're going to answer questions like, how do we interpret the inversion results? How to QC resistivity inversion results? What factors determine the depth of investigation? Okay. You can share your screen, Jair.
Let me know when you can see it. So far, no questions. Let me check. Okay. Your well reference, Sati Mustafa. Is your well reference a vertical well? It can be, but also you can have for the reference or the type well or the offset well, resistivity profile you can use from a vertical, from a low angle, or from a combination of low angle and high angle. Keeping in mind that the responses that resistivity from waterline or from inductive against traditional waterline are different. So just to let you know, but yes, you can use any type of reference or type of reference resistivity profile as an input for creating a forward modeling model. Okay, so let's try mimic a real job. As you can see on my screen, we have a scenario. We have horizons and a thickness here, a top of a coil and a base of a coil. So you can see the thickness. You can see a well plan in the blue, right? And the current wellbore drilling, or about to be continued drilling, in black. And we have a target line, which is an implementation on the software on our star steers. So you can guide the steer based on that line vector to communicate with the directional driller. And also you see on the left on the right side, sorry, the TVT correlation. So as I can move my model, you can see that all the logs overlapping the type well logs in the back is trying to match. So the first assessment is to try to match, and you can see how, as Rómulo was explaining, you can see the forward modeling changing right there. It is populated automatically with the current model modification based on my apparent or my thickness change in regard to the horizons that I use as a reference. So you can see if I make a change in that apparent dip or in the vertical positions again against the current type web reference logs, you can see that the logs are changing, right? So let's make the exercise of landing a well. So I'm trying to find a correlation in between the current logs, which are the red thick line overlapping the dashed lines in behind. So if I go up, they change the position. If I go down, they change the position. So at this point, I just find the correlation. So I think, based on my experience, that my top is going to be on this TBD position or TBD sub C position. So I can correct that, like the guidance for the directional drilling, to continue drilling. I also, as the highlight in the webinar, it's to use the whole tools that we have available on the software, or not only the inversions which come from an azimuthal resistivity tool, but also all the different logs, the azimuthal gamma ray logs, which provides an image. You can see here the features, and you can also use that as an input for the interpretation. If I use the sinusoids features, you can use that information as the apparent dip information. You can see the symbols here over the wellbore. If I change that sinusoid interpreted, you can see how the apparent dip is changing all the way. So I can use all the different tools in the software. Also, I have the seismic. You can see in the background a seismic that you can plot in behind in the curtain, Geosteering curtain. And also you have the aid of a grid from the seismic or from any information that you have available on your area. So here you can see that the wellbore was planned to drill below this grid, but currently it is not right there, the position, and it happens so often in the real life that the grid is not matching your current position interpreted. So then after that, you can correct this grid against your current horizon interpretation. So let's make a simulation on the real-time data. I'm going to push some data into the project, like drilling, like mimic drilling. I'm going to reposition my target line based on the current interpretation I have, so I can extend that. You can see that inversion is running in the background based on the real-time basis that I have. You can see the shades or the changing in the palette colors. The blues and the lighter blues are mean based on the scale of colors for the conductive boundaries, and the reddish are representing, or the orange color shades are representing the high resistivity or my target. So based on this, you can make interpretation based on the apparent dip, and you can also change the horizons. You can break the horizons. If I go back to my geosteering mode, I can change or interpret new sections, like modifying this, like you can see that I can break, and also here on my TVT section, you can see that my interpretation is moving around the segment or part of that segment logs. So you can make interpretation and reposition based on that your target line and make decision ahead in the structure. So I can go ahead and reposition based on that. I just discover that I am having a break in the trend down deep, and I can check that with the directional driller. I want to adjust my trajectory down. So the next step is going to drill the next interval, populate with more data. You can see I can extend my data, my new drilled data. I bring the trajectory down, and then I can continue with that. Okay, so if I break my segment, I can populate different sections on the TVT and make interpretation based on that. So that's how we can perform geosteering job in the real time. So you can see here that there is a change in the structural right here. So I'm going to adjust right here like this. New segment here, and you can see how I can match my interpretation based on the different tools. Back on the images, you can continue populating your images with interpreted features, like let's make interpretations like here, sinusoids, like here, another sinusoids, right? More sinusoids. So all these together, and then continue making interpretation. You can integrate all the information available. You can see here that there is kind of a displacement. So you can make interpretation right here in the geosteering model, right, like this, or you can do something like here, trying to match and making based on that interpretation to keep the wellbore inside your target. Your resistivity inversions is currently showing you that there are several structural changes along the wellbore, so you can identify the top boundary and the lower boundary and all the structural changes that you have. You have here like kind of displacement, like a structural, maybe a fault, or maybe a thickness change. You can interpret based on your experience. You can continue the job based on this process. The workflow is very simple to apply on this interface, and you can use all together in the single software. As mentioned at the very beginning, now that I have the inversion, I have the image, I have the structural interpretation, I can do an update on an update of the surface or the grid. The grid that I have is this brownish dashed line as an input, or the pre-job is showing that position as a certain thing. But now we have the correction right here, okay? So we are going to use our interpretation hub right here, horizon, and we are going to use that as an update for the grid. And you will have a new object created, and you can see here how the software is correcting that grid to a deeper position based on the current information interpreted from the different tools that we have available in real time. We can correct the whole thing together all at once, like trying to go deeper and moving everything, or you might click on the influence radius and you can re-update, and you see that the grid is corrected to the current position interpreted. And if you have expected not that much of an influence, you can just see that The correction is just going back into the original position of the grid. All together available in the software, so you continue doing the process for the workflow based on this information available in real time. If you have any questions, just let us know. The information that we have or generate based on this process of the inversion in resistivity is 4 different approaches of statistical results, like the most probable model, the P10, the percentile 10, the percentile 50, as a result of the inversions. And we present also an statistical means, which is kind of a combination or an averaging in between the 4 presented results. Also, we present as a result the automated QC of the inversion, which are understood as the misfit. So the misfit is presented as this black line along the wellbore, as you are comparing, or the software automatically is comparing the results of the inversion against the real-time data and how they match. If they are having like a good match, the misfit values are going to be close to 0. The perfect match in between the inversions and the real data is going to populate a 0 misfit, but it is kind of impossible to have that. So for evaluating this type of inversion, the closest to the 0, the better the inversion explaining the data as an input. This is a mathematical results explaining the azimuthal resistivity data. So you then, after have these mathematical results, you need to bring them into the geological context based on your experience or the knowledge that you have of the area. We have in the interface, we have different ways to, or approaches to have an inversion results. We have included an stochastic approach, which is going to be relying solely on the data themselves and the well path. Okay, so the inversion is going to be not biased by any user knowledge, or the geological knowledge is not going to be like biasing the results or guiding the results of the inversions. And then we have an option to base it on an error model like Rómulo showed before. Let me just bring that here into the screen back. We have an error model. We have an error model, right? There's going to be, right, the low resistivity, high resistivity, and again, like water or less low resistivity, let's say. So we have like two boundaries, 3 layers. So we can use that error model input as a guidance for the inversion results. So the only thing that we have to do here in the interface is to choose that error model as an input, right? This is a guidance of the inversion, so the results are going to be biased by the user knowledge of the area based on a type well or several type wells. As Rómulo mentions, you can customize this model. If you have, like, let's draw here a type well in this position with a profiling resistivity with very high resistivity, but then you have a type well around this area with a different profiling resistivity, low contrast, you can also customize that, and the model will have that as an input for the resistivity inversion, okay? Because you can customize every single segment all the way along the well path. In addition to this, we have included in the software change in the speed. So we have 2 different speeds of calculations. Let's say that depending on the approaches, you will have in the regular version So let's say the full modeling algorithm evaluation. So the inversion will evaluate as all the models possible for the inversions. So it will populate your inversion results with a better results in quality. Then you have an express versions, which is an algorithm with reduced amount of models evaluated during the inversion process. So less amount of model evaluated that brings you into the same, mostly into the same results. Let's bring it back again here. The inversions, you can see the continuity of the boundaries, but with less amount of model evaluated. So that's why the inversion is representing a faster results on the inversion. Okay. We also have the option for a server settings, so we can run these inversions on the cloud in a high performance computing instances. So for faster results, you can use the cloud environment and having back the faster results. Any questions, please let us know. So far, this is how the algorithms and the workflows present the results for you and ready to be used as an input for your geological assessment and drill the wells and complete the targeting of the lateral sections. Let me go into some real cases that we wanted to share with you. This is in red, the well pad, the actual well pad, and you can compare against the well planning, right? You have in the background a resistivity model based on the type well that you have here. This dashed black line is representing that resistivity profile. And overlying in the TVT and in the horizontal tracks, you have the resistivity data. In the first two tracks of resistivity, you have the both resistivities, the phases and the attenuations. Then you have here the geosignal of that azimuthal resistivity tool. So you can use this information again based on a horizontal geosteering core time. You can represent the horizons and make interpretation based on that. You can change your structural model and you can see how the TVT correlation is not very well right there, but you can change that and try to find a solution based on the TVT approach, strat-based methodology for trying to look for a correlation and guide your steering process. But also you have here the forward modeling. So with the forward modeling in resistivity is presented as Rómulo exhibit at the very beginning of this presentation. You can see in the dashed black overlying the real thing. Again, I'm going to move my structural and you can see how they are differing from the current situation. So based on that, you can steer as well your wellbore. So you can do crazy things like this and you can see how the model is providing you what will be the responses of the logs, and you can try to find a solution on this assessment. And then you can also use the inversions in real time. We have performed here inversions for this case. You can see the shades of greens and yellows in this case for the conductive zones and the reddish and oranges as the high resistivity, and you can see the boundaries depicted around this area here. Then you go into the target, then you are depicting here a consistent boundary on the top. So you have here the boundary below. Let me draw here lines. You can see here the boundary below right here. And then as the tool gets away from that boundary, start to populate the boundary above, in this particular case, with these constraints for the inversions. This is an stochastic inversion. So again, here you can see the boundary below, and then again here, the boundary above. So this is an stochastic approach, but you, as mentioned, we have the option to present the deterministic approach using the guidance of an input model in resistivity, and you can see better results right here. As you can see, you can depict in the previous, I just draw this line because we are seeing only from the results of the inversion one single boundary, the closest boundary to the well path. But now we are able to see the secondary boundary with different amounts of uncertainty, of course, but we are capable of the peak boundaries around here and around here. And also we have this area depicted in the stochastic, but also on this deterministic guiding the model, you can see all the way this boundary also. So these are the two approaches that we provide as an option for having an interpretation in the azimuthal resistivity algorithms. In addition, for the QC of the logs of the inversions, we can plot our inversion results for our model logs. So these are the logs that we generate based on the model delivered by the inversion algorithms. So you can see here that there is an overlapping of the logs. In this case, in this track, we are representing the forward modeling from the inversion results against the real data or the input data. You can see that they are matching in trends for the attenuations, for the phases here, and also for the geosignals. Very close. And then you have the confidence and misfit, as mentioned, they are like in quality, they are representing how good is the inversion comparing the mathematical approach against the real input data. So you can see that where the tool or the well path is close to the boundaries, there is an increasing of the misfit. So the algorithms has difficult to find a solution close to the boundaries because of the polarizations and different effects that the logs from the azimuthal resistivity tools can provide. But overall, you see that it's very low, the misfit, and you can see visually how the logs are matching, okay? I want to jump into another case. Questions, please. If you have any questions, you can just write on the
chat.
On the chat.
No questions
or
yet.
If you want to participate. Yeah. Another case. Let me show you here. We have the well path and we have azimuthal logs right here on these three tracks. And also we have here the input of an azimuthal gamma ray. And we run the inversions over these two type of resistivity. We have these inversions. Let me show you here. Right. So this is the results of the inversions. So you can see that this is the stochastic approach, and the well board, you can see that packs something high resistivity here and then goes into a very conductive area. drilling back in section and steer into the right zone, into the target zone, based on the azimuthal resistivity inversion result. You can see here that it starts to see something, to be sensitive to something here, so steering properly into that boundary. You can see here that there is one single boundary sorted out right here, because the other boundary is not that close to the position of the tool on this scenario. You can see here something, but it's not depicted all the way. So one single boundary. This is depending on the contrast in resistivity, the thickness of the target layer, high resistivity, and the tool specifications. So depending on the tool, you will have better or not that better depth of detection of more than one boundary. Let's continue. Let me delete this. So you can see here, depicting again one boundary above and then the other boundary below, because there is kind of a thickness change represented. So in this particular area, you can see that both boundaries likely to be depicted by the inversion, right? And here, one single boundary, here kind of one single boundary. So this is how you can make interpretation based on the changing of the shades of the colors, based on the distance to that boundaries, based on the continuity of those boundaries. You can define an apparent deep changes, and you can steer based on that information results. Any questions? I want to show you another case with ultra deep azimuthal resistivity tools. This is the previous two cases were representing tools that are in the ranges from 20 to 25, 30 feet in depth of detections. For this particular case in the screen now, the tools are capable of solving or have sensitivity to depth of detection boundaries at around beyond 30 feet to 100 of feet or more, depending on the context, depending on the tool and depending on the scenario. Those are the ranges for these particular tools of detections. Along the black line, which is representing the lateral well path, you can see that the tool have a detection here. Let's measure here around 21 meters of this reddish body or sand body here. Then it lost the sand body, and then it's appear back again here and have the same amount of detection, around 21, 22 meters of detections, all the way to the end of the lateral section. So these tools are intended to provide you, in additions, all the azimuthal resistivity tools, in additions to the geosteering help, also helps you to integrate different geological disciplines. Like the geophysicist, you can correct your seismic model, your speed model or velocity model from the seismic. You can also have new calculations for the reservoir. So you can update your geological model. And also you can check for the lateral changes all the way around the well path. So you can estimate geological conditions of the depositions along the lateral section. Depending on the approaches, you can have different levels of useful information for all mentioned. I think that's all I have for mentioning. Any questions on the chat, Rómulo, or maybe anything
well,
that you may add?
not much questions here. I just want to add, like, just bear in mind, like, the resistivity inversion and all this process. So it's based on fluids, right? So as I showed, there are places that you can detect higher the contrast or lower the contrast, also based on the tool you are using, the depth of investigation of the tool, the resistivity contrast based on the fluids, that are in the reservoir. So that's why you need to customize it or adjust or this interpretation to, or empower the interpretation with more data, as I show you, like the image log, deep peaking, the stratigraphic correlation. So all this data will enhance totally the understanding of the stratigraph position, and enhance also if you build a Earth models in the background, that you can enhance this resistivity contrast, creating a deterministic inversion. So you can compare stochastic, deterministic, and your model, basically. So, well, this is like so as I was saying, like, okay, all the geosteering techniques are the key, to understand or to guide the well in real time, understand in real time the structural trend of your reservoir, and also it allows you to enhance the resistivity inversions. Okay, well, there is let me check if there is a question here. Another question. But I saw there is a question about if we will share the PPT. We are not sharing because there is not much information in the slides, as you could see, but this video is going to be saved in our YouTube channel. So Rogi, we have our YouTube channel that you can find. So just type Rogi in YouTube and you will see all the webinars. Also, it's going to appear in our knowledge base website.
There are questions, Rómulo.
Okay, now I can see there are a few questions here. Great.
Okay, yeah. The forward modeling algorithms and the inversion algorithms are developed in-house. So it should be very close to the tool vendors, but they are different approaches. Do you have an algorithm for the latest version of the vendor tools? Yes, for most of the tools, we are in the path to implement for the recent additional tools from the vendors. But we have for the most of the vendor, currently we have 6 tools included in terms of azimuthal resistivity tools, and we have all the algorithms created based on the tool specifications. How quickly can you deliver real-time inversion results? We are using that Express, and as you can see on the real simulation that we perform, the results are very, very efficient. But let's say that we can just, for a tool like providing 100, 120 feet an hour, we can perform the inversions very efficiently. Even we can run a second inversion for evaluating different constraints on the models.
Yeah, and also we can connect to the HPC to speed the calculation.
Yeah, you have both options, but yeah, we can drill. Just let's say we are, depending on the telemetry for data density from the downhole tool telemetry, you need to evaluate the ROP. So, but for 100, 120, 150, you can run Express and efficiently, and you have inversion results super quick to make an assessment and make decision based on that. How many channels? You can include as many as you need. From downhole, depending on the tool provider, you were very right. You will have different amount of shared real-time logs. So for some of the tools, you can share like 8 logs in real time. Some of them can go up to 12. 16, 20 logs in real time. For ultra deep azimuthal resistivity logs, you can have more than that, but you can include as many as you need. Of course, this is going to impact the amount of time taken for the inversions. I need to mention that the 150 or 120 feet an hour is for the deep azimuthal resistivity tools. For ultra deep azimuthal resistivity tools, you have a slow ROP because of the telemetry and all the concerns related to the operational. So based on that, also the inversion will need to be taken into account the time and the amount of logs to be included on the algorithm for the inversion. But you can use as many logs as you have in the real time or from the memory. Is it possible to run 2 inversions simultaneously? Depending on the assessment. If you have like 2 licenses on the resistivity, you can run it to computers on the same project. But you, on this particular, you just click on the start button of the inversion and you can run one single inversion on the express mode and then have the time, enough time to run a second assessment on the same interval, right? We are looking to that possibility or that option to be implemented, like running 2 inversions, but it's still not implemented.
Yeah, not a different computer. It's same computer, but different projects, right? Yeah.
Yeah, same computer, different project. Yeah.
And well, the difference of the algorithm. I mean,
what are the difference? I think it is the mathematical approach, like the penalties, like the optimizations, like the switching in between the stochastic to deterministic, the stabilization steps on the algorithms, but still the same approaches for the algorithms with, of course, mathematical differences.
Yeah.
It is possible already one based on input horizon biased and another purely. Yes, it is possible to run 2 inversions, but not simultaneously as mentioned, but one pure stochastic or based on the data and the wellbore, and one like deterministic, like having the input of the horizons or the air model customized. Yes, we can do that. Could you import real-time logs or inversion results from other vendors during drilling? Yes, we can import directly from WITSML or stream it directly from WITSML, or we can have an import from the last file or the list file or WITS through a device that we have that is the solo box, or we can use any information in any format information like TXT. But yes, we can do anything like import all the real-time logs. And also for the inversion results from from the vendors, they can export in SegWi format for the TBD, and we can import that into our software, and the opposite. We might export these results from the SegWi format into different platforms using the SegWi format. Yes, we can do that.
Perfect. I think everything is clear.
Any other question, Mr. Guyen? Any other questions? Okay, I think we have it completed. We overpassed 5 minutes. Sorry for that. I appreciate you all joining our webinar. Oh, there's one more question typing. Oh, not a problem. I hope you enjoy it, and you have another questions, just let us know. You can just always communicate with Raji, and we are always happy to answer your questions. Anything else, Rómulo?
No, everything else. So thank you so much, guys, for joining this meeting. I hope you enjoy it. And yeah, you can check the video in our website in YouTube and in our Rogi knowledge space. Okay. Have a great day, guys.
You all have a great day. Thank you very much.